Welcome to lecture number 32 on validation. So we want to talk about the concept of validation. And there are three parts of today's lecture. I want to talk about what do I mean by validation. And then I want to introduce the properties of validation error. And then I want to look at the application of validation in terms of model selection. I want to talk about the basic concepts. And I want to look at some case studies. And then finally, in the third part of the lecture, I want to talk about validation in terms of regularization. So let's start by looking at this learning diagram. This learning diagram should look familiar to you now. Now we realize that in this learning diagram, there is a distribution Px. And this Px is going to generate all the training samples. And in addition, it's also going to generate the final hypothesis of G. So what we are going to do is that we want to evaluate this model using what we call the validation. The validation will provide us a technique to look at what is happening during the training procedure, and we want to get some score during the training procedure, and that can be used to help us and guide us to understand how we choose the regularization parameters and also different types of models. So the concept of validation goes as follows. You start with a data set D, and then you are going to break it up into two halves. The first half is called the validation. The second half is called the training. Now, normally when we think about the data sets, we will just say that, okay, I'm going to use all the data points in the data set for training. Validation says that don't do that. Start by breaking up the training data set into two halves and reserve some of the data points for validation. So what does validation buy you? Well, and what is the generalization bound of validation? And how do we use this data set of validation? And is validation cheating? And what do we do with this concept called cross-validation? These will be the questions that we want to analyze. So let's first talk about the role of validation. Suppose, let's look at the generalization error. The generalization error is written in this way. You have the outsample error, and then you have the insample error, and then you have a term called the overfit penalty. Validation says that I want to look at this term, okay? I want to have a validation estimate of my outsample error. And is it the same as the testing error? Well, the testing error says that I also want to have an estimate of my outsample error. Now, there is a subtle difference between validation and testing. In testing, you're using the testing data set, which is something that you are not allowed to see during your training procedure. The validation is a data set that you design and then you split from the original training data set. So you will be allowed to use the validation set. So the difference between the validation and the testing is that while they're both trying to estimate the outsample error, the estimation in the testing case is based on the testing sets, whereas the estimate in the validation is based on the validation set. Normally, the validation set is very small, and the testing set is usually very, very large. So the testing, you cannot use the testing set in any stage of your training. If you ever use that, then you are cheating. Validation, you are not cheating because you are still using your training set. You're just splitting the training set into two halves. One is for training, the other one is for validation. So creating the validation set can be done as follows. You start with a data set which contains all the n samples, and then you say that I want to allocate k samples for validation, and then the remaining n minus k samples I will just use for training. And so when you try to use this n minus k samples for training, you will be able to get a hypothesis, which I call it G minus. Now, I put a G minus here to denote that it is a hypothesis obtained by subtracting some samples. G minus is not the same as G because G it will be using all the data points from the entire data set D, and G minus is only using the training data set. And G minus is not necessarily the same as the final hypothesis that you will eventually use. What do I mean that? Well, you use the training data set here, you train, and then you get G minus, and then you use validation to choose the parameter. Afterwards, what you can do is that you can combine the two together and then retrain one and then return that as your final hypothesis. This will help you recycle the data. You're not going to waste the data. So what does validation tell us? Well, our goal here is trying to define a term called the validation error, and we want to analyze its statistical properties. So the difference between validation error and training error and testing error has to start by defining what do we mean by the validation error. The validation error is defined in this way. You take your G minus, which is your hypothesis learned using the training set without the validation part. You evaluate your error using the samples xn. Okay, so you get the xn, and then you compute the error. So the each E will be the point-wise error for each xn. And then you sum over all the xn's inside your validation set. So now you're not summing over all the training set because you want to evaluate the validation error, and so you want to evaluate all the xn's from the validation set. This validation set contains k samples, and so you take the average, you divide by 1 over k. And so this is the average error over all the validation points in the validation set, and it's a point-wise error. Now, if you use a classification, then the error will be given by this indicator function. If you do regression, it will be a square term. And so you want to analyze what? Well, you want to analyze this term. This is a validation error. It is a statistical quantity. Why? Well, this is because anything on here, this is a random variable. It is random because your xn is random, and therefore the error that you generate is also random. And so you want to talk about its distribution. In particular, you want to talk about its mean and its variance. So let's first look at the mean of the validation error. So let's look at the mean. We want to show that the validation error is actually an unbiased estimate of the outsample error. In other words, if I take the expectation of my validation error, I'm going to get the actual testing error, the outsample error. Let me show you why this is indeed the case. You start with this validation error. Now, remember that this validation error is chosen according to the particular validation set that you have in this equation. So, because you're choosing over a different validation set, you want to take the expectation over all the possible validation sets in order to calculate the overall error. Okay, so here is what we mean by the mean of the validation. And so I want to take the expectation of the validation, and I can show you that you keep the expectation outside and you put the definition of the validation into this equation. And then you can move the expectation into the summation because the expectation is just a linear operation. So you can make the expectation inside. And then now you can see that what is the definition of this validation set? The validation set is defined as xn and f of xn. And so they were both depending on your xn's. And therefore, you can replace the expectation over the validation by the expectation over the xn's, where xn is drawn from the distribution, underlying distribution. And so now, what is the expectation of this point-wise error with respect to the expectation of xn? That is nothing but just the outsample error. Okay, because now the expectation is taking over all the possible xn's from your distribution px. and Px is the overall population density. And so when you try to take the expectation over xn, that will give you the outsample error. The outsample error is evaluated on G minus because here the error is computed with respect to G minus. So you have this outsample error G minus, and then you sum over all the possible xn's. But now look at this term, there is no xn's involved, and so you're just summing this number k times because there are k samples inside your validation set, and you divide by k, so that will give you E out of G minus. So you look at this equation here. In the beginning, we want to look at the expectation of your validation error. And at the end of the calculation, we show that the validation error, when you say expectation, is just the expectation of, it's just the outsample error. And that means the validation error is an unbiased estimate of the testing error. Let's now look at the variance of the validation error. So we can define the variance of the validation error by just taking the variance with respect to your D. And then, we ask, how does this validation error's variance depend on K? Now, what do we hope? We hope that as K grows up, then the variance should go down, because when you have more and more samples in your validation set, then the variance should in principle becomes less and less. There shouldn't be any fluctuation of your validation error. So let's do some calculation. So let's start with this sigma square of validation. So this is the variance of the validation. And you can put into the definition of this validation error. And then by linearity and also the independence of all the samples, you can show that it is just the 1 over k squared. It becomes k squared because you're taking the variance. And then you have the sum of all the individual variance of the pointwise error. And then these I define it as the sigma square of G minus. Now I can call it as just the G minus. There's nothing depending on xn because I have already taken the variance over the entire data set D eval. And therefore, I will left with taking the summation of all the sigma square of G minus. And since there are k validation samples, that will give me 1 over k times sigma square of G minus. And so as long as I can compute sigma square of G minus, then I can show you that the variance of the validation is linearly decaying as a function of k. And what it means is that as I have more and more k, there shouldn't be any fluctuation of your validation error. And the validation error will eventually converge to the mean. And the mean, as we have shown in the previous slide, that would be the average of the testing error. Okay, so that is the testing error, and that is the ultimate testing error that we want to get. And if you have k going to infinity, you do not have any variation, then because of unbiasedness, that means the validation error will actually converge to the actual testing error that we want. So now let's do some additional calculation trying to bound the sigma square. So if your validation error is pointwise error is defined for the classification, then you can show that the validation error, the variance is 1 over k times sigma square of G minus, and that is just the variance of this pointwise error. And let's put the definition of the pointwise error into this equation. Then you have this indicator function, which is either 1 or 0. In other words, it is a Bernoulli random variable. And then you can calculate its variance. The variance of a Bernoulli random variable is just p times 1 minus p. And so if it's Bernoulli, you can show that the variance is upper bound by 1 over 4. And therefore, you can bound the variance of the validation error using this union bound of 1 over 4k. And therefore, as k goes to infinity, you can guarantee that the variance will go to 0. So does validation error generalize yes, it is in itself, it is a random variable, and therefore it fluctuates. The mean is this quantity, and we show that it is an unbiased estimator. And then we show that the variance is this, and it's decaying as a function of 1 over k. And so the previous slide says that the expectation of the validation error is just the outsample error. Now, outsample error is something that we really want to get. So what we have here is that the Hoeffding inequality. The Hoeffding inequality says that the outsample error is something that we want to estimate. When you do the training procedure, you want to see whether my choice of my regularization parameter is good or not. Then I want to evaluate. Then I'm using this validation error. I calculate the validation error. If the validation error is a good representation of my testing error, then I will be able to use it. And then I can do the model selection and also the parameter selection based on the validation error. Now, if the validation error has a lot of variation, then this is not a good news, because then the validation will have too much fluctuation in the validation error, and that is not a good representation of your testing error. The equation that I'm showing you here is that from the Hoeffding inequality point of view, it says that the outsample error is upper bound by the validation error plus 1 over the square root of k. This comes directly from the fact that you're only using the G minus. Okay, and then because you're evaluating inside your validation set, and that will limit the number of training samples that will limit the number of samples that you can use to represent the testing error. The difference between this Hoeffding inequality and the previous Hoeffding inequality is very, very subtle. In the training procedure, when you do the Hoeffding inequality, you have E out less than or equals to E in plus 1 over square root of n, where n is the number of training samples. And here you're limiting by the number of validation samples. And that's why, by understanding the mean and also the variance, it seems the variance of the validation error is dropping as a rate of 1 over k, and therefore as k goes to infinity, your validation error will be a very, very good upper bound of the testing error. So as k grows, the validation error actually generalizes the testing error very well, and therefore, as you have a lot of samples in your validation set, you will be able to estimate the testing error. So should we use a very, very large k, or should we use a very small k? There should be a clear discussion here, because if you use a large k, then in principle, as what we have just shown, then you will be able to get a very, very good bound. However, if you use a very, very large k, then you may not have enough training samples for doing the actual training. So there should be a trade-off between the number of samples that you allocate to the validation set. So large k is good, but can k be really, really large? It's not, because ultimately what you care about is the expected validation error, and as the validation set grows, this curve will change, where you can see that the shaded region, that would be the variation of the error. And so there should be an optimum operating point, which is somewhere in the middle, that you want to choose the k from. Now, we should also be aware that when you do the validation, that we should also be able to reuse the k's. Because if you only use the n minus k samples to do the training, then you will not be able to leverage the other k samples for the validation when you try to retrain. So because we're doing this validation, this is still inside the training procedure, you are allowed to reuse the k samples. So first of all, you use the validation set to calculate the validation score. And then you use the validation score to choose and to guide you to choose a good hypothesis. And so this is a diagram showing you how. You start with the data set n, okay, so that contains n samples. And then you split the data sets into training and also validation. The training, when you do the training, you'll get a G minus. And then you use that G minus to evaluate. You use k samples to evaluate the G minus. And then you get a validation score. And then once you get a score, you make a decision of what kind of parameter and then what kind of model that we want to choose, and then you go back to here, and then you choose the final hypothesis G, and you report that. Okay. The rule of thumb of the choice is k equals to n divided by 5. Now that's not straight. That's also not mathematical. That's just some heuristics that we have been observing in practice. Normally choosing between n divided by 10 to n divided by 5 is usually a good range.